These are the notes for Unit 2, Day 3. And for this next class, please bring your textbook. You're going to need to refer back to it as we're doing the activity in class regarding these notes. So the notes start on page 11, I believe, of your note packet. And the title for these notes is called Applying the Power Rule. So our essential question then is, what shortcut can we replace the limit method with? So the limit method, you've done that a few times. You're going to do it once more. And it's time consuming. And it's got to be redone every time you change the point. So it's ineffective. We need to replace it so that we can do this faster. And so that's what we're going to be moving towards today. So I mentioned this in the last note section. I'm gonna kind of drive this home almost every class. When I say derivative, you think slope, and when I say slope, you think derivative, right? And when we use the word slope, we're really referring to slope of the tangent line to the curve, right? It's just a lot to write, so I'm just going to shorten that up, right? Slope at a point, slope of that tangent line. You're starting to think derivative. Okay, those two are synonymous. They are synonyms. They mean the same thing. Okay, this actually isn't in your notes. It's just a short discussion, but it's just background information that we need you to have so that when you come into class with your book and your calculator, that you have this background information to do the activity. Okay, so let's talk about functions. We're going to first talk about constant functions. So what does that mean? A constant function. Well, constant means the value doesn't change. So when we're talking about a constant function, we're saying the y value is always the same. It's constant, right? Like f of x equals 5. That's a constant function. What is its slope? I mean, we could do a rise over run, right? We could do an algebra calculation, but I don't think you need to in this instance. So take a second, think about it. What is its slope? Get a value. Slope is 0, right? So if the slope is 0, what's the derivative? It's also 0, right? When I say slope, you think derivative. Where is that true? At this point, at this point, at this point, at this point, at all points, right? We didn't need to have a point in particular. We know that for a constant function, the slope everywhere is the same value. So the derivative everywhere is the same value. Let's try another one. G of x equals 1. What's its slope? 0. What's its derivative? 0. Where? Everywhere. H of x equals -2. What's its slope? 0. What's its derivative? 0. Where? Everywhere. So a couple of things come out of this. If I have a constant function, its slope is, answer that question, 0. Where? Everywhere. So its derivative is 0. Where? Everywhere. So that's kind of cool. We no longer need to do the limit method for constant functions. If I give you a constant function, you can tell me the derivative right away because you know the slope everywhere. The other interesting thing is this. I gave you 3 different functions, right? How many constant functions are there? There's infinitely many constant functions, right? So we know the answer to infinitely many derivatives right now, as long as I give you a constant function. So there's lots of functions that have the same derivatives everywhere. That's going to happen. Okay, what other functions have constant slope? So think about that algebraically. How about lines? Right, y equals mx plus b. So what's the slope of this line? It's 5, right? We can find that a couple different ways. We can see it here, y equals mx plus b. We can count up 1, 2, 3, 4, 5 over 1. We can do that anywhere. It's going to be 5. What's its derivative? 5. When I say slope, you think derivative. How about this line? G of x is 1x plus 2. I shouldn't have put the 1 there. I should have just put, or minus, excuse me. I should have just put x minus 2. What's its slope? 1. We can see that again, either graphically or algebraically. What's its derivative? 1. Where? everywhere, right? The slope is 1 here, the slope is 1 over here, it's 1 everywhere. How about this line? H of x equals negative 2x plus 4. What's its slope? Negative 2. Don't pick the other number, right? What's its derivative? Negative 2. Everywhere. So now you know the derivative, how to find the derivatives not only of constant functions, but any linear function that I give you, you can find the derivative of without doing the limit method. That's pretty nice. Okay, what about higher order polynomials? So for example, how about x cubed minus 3x squared minus 6x? So what is happening to the slope of that tangent line as I traverse this function, as I sweep across this function? I'm traversing this function. I can almost get a slope of 0 there, right? I can almost get it to be horizontal. Trying, but it's tough. But that slope is changing. It's not constant anymore. Now the slope depends upon where you are. It goes from a positive value to a negative value, has a couple 0 values, right? Back to a positive value. It's steep sometimes, it's flat sometimes. It depends upon where you are. So what's its derivative? Well, now we have to do the limit method. And it depends upon what location we're looking at, okay? So while the expression can be found, the value of the derivative depends upon its location, right? We see lots of different values for the slope of that line. Okay, the steepness depends upon location. Like we can get a really steep negative value somewhere about here. It's as steep as it gets, then it starts getting flatter again as it goes towards this valley. We can definitely look at that and say, hey, I know 2 points where the slope is 0, right? I can draw a horizontal line up top here and down at the bottom here. So we can at least give you 2 values. But the rest of them we need the limit method for. The limit method for this is messy. Okay? So yay, we get to do the limit method on something messy. Okay, so now we're starting our notes. Okay, so back to the essential question. What shortcut can we replace the limit method with? Well, we already replaced the limit method for constant and linear functions with a shortcut because we know these slopes are constant here. So we know that if f of x equals 5, its derivative is 0 because its slope is 0. If f of x equals 8, that's a constant function. What's its slope? Then what's its derivative? Also 0. How about here? F of x equals 3x. What's its slope? So what's its derivative? 3, right? The slope is right here, mx plus b. B just happens to be 0. Here's another linear function. What's its slope? Right, mx plus b, 4. So what's the derivative? 4. So we know how to find, we've already got a shortcut for finding derivatives of constants and linear functions. By the way, constant functions are linear, so we could probably just say, we know how to find the derivative of linear functions. Okay. Now, this is where we come to the class activity. Let me back up, right? I said finding the slope of, finding the derivative of this function is super messy. I'm not going to make you do a function that messy. Okay, but we are going to do these 4 functions. So you have a pod assignment, right? Those are the letters hanging from the top of the ceiling. So you're either in pod A, B, C, or D. Okay, and so if you're pod A, you're going to do the limit method on this function. If you're pod B, you're going to do this one, and so on and so forth. We're doing this in class though. Okay, so I give you some space in your notes. That big space is for the class activity. You don't have to do that at this point in time. Okay, so when we get into class, we'll get into our pods and do the limit method back on these functions. And we will, by the end of class, be able to have a shortcut for functions that look like this. Super exciting.